Hi everyone, Dr. J here, and in this video we're going to just introduce the topic of geomagnetics, and this is going to be basically about the Earth's overall magnetic field. So we're no longer talking about kind of the conceptual, theoretical ideas behind magnetics, but now we're looking at the Earth itself and trying to understand just a very basic bit about what the Earth's magnetic field is like. Now, I'm not really going to be able to go into too much detail here in this presentation because we haven't introduced all the mathematics that we'll need to be able to understand that. But the basic idea that we want to cover is that Earth behaves to some degree like a giant bar magnet. So the Earth, of course, we use compasses to navigate on Earth, and that's because the Earth has a north and south magnetic pole. And so in some ways, the Earth behaves like a giant bar magnet, although it's not. The magnetic field of the Earth is thought to come about from currents in the Earth's liquid outer core. We're not going to go into detail of all the geological aspects of that. But it is true that we can roughly approximate Earth's magnetic field as coming from a bar magnet. But there are variations. There are things that affect the Earth's magnetic field that we need to be aware of. So, for example, the solar wind is a stream of charged particles from the sun, and those interact with the Earth's magnetic field and distort it. So you can see here, this is pretty well known. You've probably seen this before. The incoming solar wind from the sun causes the magnetic field to be compressed on the sunward side and extended out on the far side of the Earth. There's also a couple of radiation belts around the Earth which are caused, or which hold charged particles. These are the Van Allen radiation belts, and those are also related to the interaction of the solar wind and Earth's magnetic field and charged particles in the upper atmosphere. And if we have solar events like solar storms, you can additionally distort the magnetosphere beyond just the constant solar wind. Right, so there's lots of things that influence Earth's magnetic fields, and there is a regular cycle to some of these effects. So, for example, the sunspot cycle is correlated with the number of solar storms, and that those storms are going to impact Earth's magnetic field. There's also, like we said, currents in the outer core of the Earth, and those result in various changes to the magnetic field. So you put all this together, and we have a rather complex magnetic field, actually. It's not just a simple bar magnet, although, again, we can kind of approximate it as a bar magnet to first order, but you can see there are these variations. And in particular, you can see some pretty big variations in the intensity of the total magnetic field, which is what this graph is showing. So some of the higher values here are around 65,000 nanotesla, and some of the lower values might be as low as 25,000 nanotesla. So just in the intensity of the total magnetic field around the Earth, we can have some pretty big variations. And these variations change through time. This is what's called true polar wander. The Earth's magnetic poles move around, and not just the magnetic poles, as you can see, but the actual, in this case, we're showing declination. So declination in degrees east. Declination we'll define here in a minute, but it's the difference between the direction to the Earth's magnetic pole and the Earth's true geographic North Pole. We'll talk more about that in just a second. So Earth's magnetic field is changing through time. Overall, yes, it kind of behaves like a bar magnet, but there are a lot of details, and it's time varying that make it much more complicated than just a simple bar magnet. So as I mentioned, there is a difference between the Earth's true North Pole and the Earth's magnetic North Pole, which is related to the Earth's magnetic field. And the difference between those is referred to as magnetic declination or variation. So you can see degrees east or west of true north. Actually, here in Missouri, we're very close to the agonic line, and that is where the declination is 0. So and I'll show you a map here in a second. So we can calculate those quantities there, as you can see on the screen. But here's a good example, a good figure to kind of illustrate this. So the agonic line is where the magnetic North Pole and the true North Pole are in line with each other. So there's no difference in the direction to the two of them. But then as you go to one side or another of that agonic line, you can see that the variation can be quite large and change a lot pretty quickly in space, depending on where you are and where you're going. So if you're using a compass to navigate, maybe you're flying an airplane across the country from one side to another, so your compass is pointing to magnetic north, and that's not going to change, but where that true magnetic north is relative to true north is going to change quite a lot as you move across the country. Now let's just get some terminology out of the way. We've already talked about the total magnetic field B. This terminology is a little bit confusing because we were also talking about the magnetic field H as somehow proportional to B, and we talked about how there's an H which is like B, but it has no effect of the magnetic currents, and it's scaled by a constant. This H is different from the H that we talked about before. So again, I apologize for the terminology. In this case, this is the horizontal component of the magnetic field. So we have a total magnetic field vector at some particular location. So in a geographic and an Earth reference frame, we need to think about our coordinate systems. And in here, we're defining geographic east, north, and down as the local coordinate system. Our magnetic field, total magnetic field vector is some vector in that coordinate system. And then we can imagine the horizontal component. And then, of course, we would also have a vertical component of the field. And just various ways to describe that total magnetic field intensity, or total magnetic field vector, I should say. We can also think about the declination and inclination of that, right? So there's our declination definition that we had before. This is the difference between the magnetic North Pole and the geographic North Pole. And then the inclination is the difference between that horizontal direction and the actual total field vector. And you see the word intensity there. The intensity doesn't refer to the vector itself, but just the length of that vector. So that vector has some length, and that's what we mean by magnetic intensity. So again, this is just various ways to decompose. Remember, magnetic field is a vector. So it has, in 3 dimensions, it would have 3 components. And these are various ways to decompose the magnetic field into this geographic coordinate system. But as we mentioned, the Earth does have a true North Pole. That's its rotation axis. And how the magnetic field changes with respect to that rotation axis is kind of interesting. So here's a graph which shows the history of where the Earth's magnetic North Pole was located going back in time. I think this starts in 1590 and goes up to around 2020. So a little bit, couple of years old, but you could see that the actual position of the magnetic North Pole, has changed quite a bit. And in fact, the rate of change and the direction that it's moving has changed quite a bit through time. And of course, this is also true going back in Earth's history. This is the location of the true North Pole, approximately, and the approximate location of the Earth's magnetic North Pole, just from a Google Earth screenshot here, showing the relative difference in those 2 locations. And in this particular case, they're not too far apart. As you've seen from this other graph, in the past, that the 2 poles have actually been further apart than they are right now. So let's talk now about a model of the Earth's magnetic field. So the Earth's total magnetic field, it's not a pure bar magnet. We can't model it as a single magnetic dipole. It has these other complexities in it. And you can see, again, this is the total intensity of the Earth's magnetic field. And as I mentioned, this total field is changing in time. So we can actually look at the rate of change of the Earth's magnetic field in nanotesla per year, and various places are changing faster than others. So the Earth's magnetic field is complex. It's being affected by currents in the Earth's core, solar cycles, all sorts of things. It's a complex thing. So what we're going to do in this class, talk about in this class, and what the international community has done is created a model of the Earth's magnetic field, because we don't really have a way to measure this field continuously everywhere on Earth, right? We can make measurements at a single location. We might be able to conduct magnetic surveys of a particular area, but we really can't, get the entire picture all at once for the Earth, and certainly not at every moment in time. And so what we have instead of that is we have a model. We have a model for Earth's magnetic field and how it's changing through time. And this is the IGRF. This is the International Geomagnetic Reference Field. We don't really have the mathematical nomenclature to fully unpack this yet, but I wanted to just show you the field, show you the example of the field, and a couple of things, talk about a couple of things related to that field. So I'm going to stop sharing my PowerPoint here and switch over to a web page. So let me pull that web page up real quick. All right, so just a few things about the International Geomagnetic Reference Field that I wanted to go over. It's a standard mathematical description of the large-scale structure of the Earth's main magnetic field and its secular variation. So we're trying to understand and model the Earth's total magnetic field. And in order to do that, we need to incorporate all the different observations, all the different data sources that we have on the Earth's magnetic field. And the way that this is done mathematically is to use the concepts that we've talked about in this class. So we have the Earth's magnetic field B. You can see here on this Wikipedia page, Earth's magnetic field B is related to the negative gradient of the magnetic scalar potential. So we're talking about, number one, outside of Earth. So we're going to assume that there are no currents that we need to worry about. And so the magnetic field in that case has a scalar potential. We don't have to worry about the vector potential. We're assuming a scalar potential. And the magnetic field is just the negative gradient of that, which again, the field is a vector. The potential is a scalar field. The magnetic field B is a vector field. So it would have three components in 3 dimensions, and you can see the 3 components there on the screen, but really you could decompose these in different ways depending on your coordinate system. Now, the key thing that is done with the magnetic field estimation, you can see here on this webpage, and I've got these linked in your PowerPoint. The key thing that's done is to decompose the potential, not the field. We're going to calculate the potential as a sum of spherical harmonic functions. Now, we haven't covered spherical harmonic functions yet. We're going to cover those in the next module, so you're going to see a lot more about this. But the basic idea here is that we've got this whole entire magnetic field. How do we model the entire field and varying in time with only data points that are maybe at a few locations? Maybe we have some areas covered, but not others. And we need to do this in continuous time. We don't have data everywhere and all the time, right? So how do we do this? And the way that we do that is by simplifying how we represent the field. We represent the field as a set of spherical harmonic functions, which again, we'll talk about later. But you can imagine these are sort of representing various aspects of the field. So some aspects of the field might be very long, kind of slowly changing parts of the field. That would be like the overall magnetic dipole, for example, might be the very first component that we would think about modeling the Earth's field with, just a single magnetic dipole. But we can also have higher order aspects, shorter wavelengths, more variability. And these different terms in the spherical harmonic expansion are going to include some of that variability. And then you sum all of those together. These are the summation signs on the webpage there. So you sum all of the terms in the spherical harmonics together, and you get the total magnetic field. So you have both the very large scale, slowly varying aspects of the field, and then the very rapidly changing aspects of the field. And we can basically adjust how many terms we keep in the summation, and we can represent the magnetic field better or worse. So I believe there's 13 terms included in the current version of the International Geomagnetic Reference Field. Just to show you some pictures of what that looks like here on the screen. This is from the British Geological Survey, and you can see various things: declination, rate of change of declination, inclination, annual rate of change of inclination, and so on. And here's our total field intensity at the bottom and annual rate of change of the total field intensity. Again, the links will be in the PowerPoint. All right, so that's just a basic introduction to the IGRF. We're going to talk a lot more about this later on in the course, and so I will see you in the next video.